Okay, it's 2 past the hour, so why don't we get started? I want to welcome everybody to this networking channel event. It's going to be a great one. This event is on lessons learned from 40 plus years of the internet, and I'm just so excited to be able to sort of. My job's just to sort of host this, but Henning will give you just a bit of background about where this started. But let me say that there was a Dagstuhl seminar that Henning will tell you about. We have some of the organizers and participants here on this topic that happened this past May. And it was just a fabulous group of people. And it's not that often as a community that we sort of get to sort of sit back and think about these big kinds of questions and reflect on lessons learned. I mean, that's sort of not what happens at a typical conference or workshop. So I'm really excited about today. So let me introduce the panelists, and then I'm going to turn the next slide after this over to Henning. So I'm going to start on the left-hand side of this screen. So Henning Schulzrinne is a professor at Columbia University. He's I have to say he's a proud graduate of the University of Massachusetts Amherst. He, in addition to his academic work, his work in the IETF, he's also done really amazing things in service at the FCC, and he's currently at the NTIA. Is that right, Henning?
Yep,
okay.
NTIA, the part of the Department of Commerce.
Right. Our next panelist, and all of these folks were either organizers or participants in the earlier event. So Dave Oran, many of you, I'm sure everybody knows everybody here, but so Dave Oran, a longtime researcher in networking in Cisco, very active in the IETF, and who's also done amazing things. He's one of these people where when he says something, it's like, I always listen to what he says because he drops pearls of wisdom all the time. Jörg Ott, also very active in the IETF, is a professor at Technical University in Munich. And Jörg, I don't know if you were the head organizer, but you were certainly one of the lead organizers for the Dagstuhl event. So thank you for doing that. Craig Partridge. Craig, I met you in 1985 when you were still a graduate student. You were working at BBN, but I think you were finishing up your PhD at Harvard. Craig went on to do tons of amazing things at BBN. All of these people, I think, have been involved in SIGCOMM in one way or another. Craig is currently chair of computer science at Colorado State University. And John Wroclawski, our fifth panelist. John's done amazing things also. One of the deepest thinkers I know about architecture. He's at the Information Sciences Institute in ISI in Marina del Rey in California. And another one of these people, every time he says something, pearls of wisdom just fall out of it. Okay, so with that introduction, let me go on. Henning, you want to take this slide?
Yep. Thank you so much for organizing this interim. This is an attempt to reflect a little bit on what we reflected on in May. For those of you not quite as familiar with the venue, Dagstuhl is a castle in the western part of Germany at the French border, in Luxembourg border, that organizes typically half-week type of seminars in a small group. So we were, Jörg, you correct me, about 30-ish people. Typically, that looks forward to what are open issues in research. The seminar was very different. We tried to do both, look backwards, because many of us have been involved in internet-related research at various layers for good part of us 40 years in some cases, and to see what lessons we could draw from that. So we've had as a community a long history of looking at future internet type of efforts, for example, in that. But I think the emphasis changed in the sense there's probably less emphasis on fundamental changes in design, but also maybe more interest in learning why the internet, while clearly technically, economically, and in terms of societal impact, one of its most significant changes in the last 40 years, why it has been so resistant to change despite all the academic and industry efforts in that. So in particular, we tried to answer a number of questions. So for example, some approaches have clearly been successful, but we don't always formulate why that has happened. What was it that despite these dramatic changes in the technical environment, that they still have aged well? Then there's often an emphasis to focus only on kind of a long-term constant, the IP layer, and not a network layer. But we also spend a fair amount of time talking about both the upper layers, applications where obviously a lot of the value add is these days, and as well as kind of forgotten but necessary components, namely how do we control and manage the internet. In some cases, the discussion was, if we could do a do-over, kind of reinvent history, how would we do that? This is obviously a theoretical discussion in the sense that we probably won't get that chance, but what should we do? Because that will also be not just interesting technically, but I believe, and that topic came up a fair number of times, is we often treat, when we teach networking, which I think many of us, if not most of us, do at some point or another to the next generation of network engineers and researchers, we often treat the network as kind of a given. It is what it is, and you just learn how it works, and you reproduce that on the exam or the project or whatever. But often useful to tell students in particular is, this is not the only path we could have taken, and we might have taken a different path if we were starting today. And as you'll see in the discussion to follow, the emphasis has been often on algorithms and protocols as kind of the key things, but many of the impacts, as well as some of the difficulties, have little to do with what's written in an RFC or in SICOM papers, but really has been about how implementations have shaped the internet. And as in what we can and cannot do is often shaped by the software that's available, the open source processes, et cetera. And increasingly, as to we are no longer in an environment where we can just do whatever, but for good reasons, almost every national and these days international regulatory body has taken a keen interest in that, simply because the internet has such economic and political and societal impact that it can't be a regulation-free environment in that. And then we have also done a number of case studies. You'll hear some example on that. Now, note in particular, and just in terms of questions and discussion later, we are not trying to establish who invented what part of the internet. That is a worthwhile effort, but not really the focus on that. It is we don't care how it got, who did it, but we care as to why and hows and maybe what else we can do. And with that, I think we can proceed to the more in-depth comment.
Okay. Whoops. John, you're up first.
Yep. Hi, folks. Thanks for joining in. Glad to have everybody here. So I want to actually start by saying something that isn't on my slides, and it echoes what Henning said a little bit. So the interesting thing is that after about 40 years of really hard work, I think of networking as kind of a teenager. It's no longer the hot new field where everything is new and everything is cool and all the fruit is low hanging, and anything you do will be an advance over what the last person did. But it's also not, the fully developed and codified engineering field that something like bridge building might be, or something like that. So we're in this very interesting transition. And that kind of corresponds, I think, to the fact that the first generation of networking people are kind of reaching the ends of their careers now. And so that's another aspect of the transition. But the thing that's interesting for those of you who have them, and I'm not one as it happens, as a teen, we're kind of in the process of learning how to grow up, right? And learning what we will do differently as an adult. than we've done when we were the hot new field. So this has a huge amount of effect on things like how we choose to pass on knowledge and what knowledge we pass on, and how we get folks to sort of understand, as Henning said, the underlying kind of principles of this thing, not just what we did. And another place where this really shows up is it, for those of you who are academic, it affects greatly the kinds of research that we need and the kinds of research that are valuable. So there needs to be more of a focus now on systematization of existing knowledge. And it's not just what new thing can we do. New is, the question that you have to ask at this point as we grow up is, where's the balance between what worked well before and what needs improvement or what could be done differently, and so on. And the fact that some of the folks who talk about, oh, I tried this really cool new network architecture and it didn't work, well, it could be that that's because you actually the previous one did something really well, right? It may just not, so it's a very interesting question. And I think this question, expressed in many different ways and in many different things, turned out to be a really key high-level focus of this Dagstuhl, which was really cool. So on to the slides. The first slide is the question that was thrown on the table was, what worked well in the internet? And so I want to suggest two answers. One is, and these were things that many people brought up at the workshop in different ways. One is this idea of incremental permissionless innovation. This seems kind of obvious today, but the design of the internet, and particularly this notion of what's called the end-to-end principle, which still applies today, even though it's more complicated than it was in 1980, created the ability for any set of people to get together and do something new, deploy a new application, without getting general agreement from everybody else, and without getting permission of gatekeepers like the phone company. And that may seem obvious to you today, but 40 years ago, that was not how things normally worked. And so that was a tremendous change in the landscape that allowed the internet to blossom where many other ideas for wide-scale networking did not. The second point is this notion of architected decoupling. And this is an architectural point. This is the point where if you have very well-defined, appropriately defined fixed points in the architecture, then things can evolve around them in a decoupled way. So the classic example here is, the thing we call the narrow waist of the internet, the sort of IP protocol thing, which allowed technologies to evolve over 40 years without affecting applications that much, and allowed applications to evolve without affecting technologies that much. And this happened because we were able to create this decoupling between different parts of the system. So the point I want to make is that it's hard to do this well. And we do not, even today, I think, have a clear, teachable conception of what a good fixed point is. And many people think it's like how many extensions you have and how much flexibility you have. And that's actually wrong, because a fixed point cannot be too flexible. So this is a place where the internet actually did a very good job. In some sense, perhaps the folks got lucky, although it's also clear when you speak to them that they had an instinctive sense of what they were doing. But it's a really important point, and it continues to apply today. Next slide, please. So, whoops, one too far. Okay, something that didn't quite work. Henning mentioned this too. The quote on the left is real. It's not apocryphal. A famous economist who was a friend of the internet and does not therefore wish to have his or her name associated with this because he wasn't, or she wasn't being critical, pointed out that when the internet was designed, people thought really hard about routing packets, and what they didn't think about was routing money. And this is a real problem for the internet style of network, precisely because of the thing that I was talking about before. There is the thing in the middle of the network, which is the service that connects everybody else in the internet conception, is a commodity, right? It's a global fixed point. Everybody runs IP, everybody carries packets. There's from a technical point of view, it is desirable that everybody do the same thing. From an economic point of view, that's a disaster because it means you can't differentiate yourself in any particularly useful way. And if you did, there's no way really to collect any additional revenue for it. So What happens instead is people start screwing around with things and they start distorting the system so that they can figure out a way to make money. And this is an ongoing challenge. This has been an ongoing challenge all through history of the internet. Back in the 1980s and 90s, the ISP, the big carriers were like, I don't understand how I'm going to survive here. I'm getting driven out of business by the guy who can do it 3 millicents cheaper. 2 days ago, the telecom companies, a consortium of the telecom companies in Europe popped up and called on the European Union to compel the big tech companies to, quote, pay a fair contribution for using the networks, which is to say they're looking for a subsidy or a flow of money into the commodity part of the network. And rightly so, because they're benefiting hugely and it's very hard for the commodity folks to make money. So this is a fundamental example of the tussle between economic reality, and it's an interesting economic reality because of course it's a little bit different in Europe and the United States and Asia, and the technical reality where the economics of the system and the strongest technical design from a certain perspective push you in different ways. You went backwards.
Sorry, just pushing you forward, John.
Yeah, no, I understand, but backwards is not the right approach. Teasing. Okay, so the one thing those were things that I think we talked about in the workshop in general. So this is a personal answer. The thing I think that we didn't think about was sort of application lifecycle, right? When an application is new and small, the key question is how you get it out there and how it's going to change quickly and how it's going to advance and sort of take over the world. And as it matures, what becomes much more important are things like optimization and efficiency and the security and stability and things like that. And so there's a sort of a qualitative shift. And you would like the network itself to accommodate both of these with its mechanisms, with its sort of support services and things like that. And this is a hard thing to do. The hard thing is to accommodate both at once. We haven't done that very well, and it's created a lot of pressure to do weird things like, run voice over HTTP and stuff. And so I think that's a place where we have work to do. I'm done.
Okay, great. I think we'll come back to that notion of tussle and the social and the economic sides of this for sure.
So hi,
Okay.
this is
Dave.
yeah. So you're going to find throughout the speakers here that we're going to recapitulate with slightly different words and slightly different emphases, pretty much the same themes. And one of the interesting characteristics of the seminar, which we hope to capture, in written form eventually, is that those nuances may in fact matter. And however, the fact that there's some core things that everybody sort of shook their heads yes on means that maybe there are some important lessons we can draw away. So from my point of view, I'd like to sort of split up the discussion of why the internet may have been so successful into 3 kind of subcategories. There's the technical aspects, the economic aspects, and the regulatory aspects. And for this, I want to go back to the early days and say, what was potentially different or special about the early days when the internet was getting built and expanding rapidly that allowed it to do so successfully? And from a technical standpoint, one thing that really stands out is that the minimal guarantees made by the packet transport that was defined for the internet allowed it to run over a wide variety of communication technologies. And something that was happening simultaneously with the development of the internet protocols was the fact that those communication technologies were themselves evolving extremely rapidly in the late 70s and early 80s. We had the beginnings of Ethernet, ATM, optical rings, cellular wireless, and the fact that IP didn't require much out of the lower layer and was easy to host over a wide variety of rapidly changing lower layers allowed the whole system to move very, very quickly and to accommodate new lower layer communication technologies as they became commercially viable, and also allowed them themselves to compete in the market in a way that did not bind the successes of a given lower layer technology to the success of an entire stack of protocols. And this comes back to what John said about having fixed points around things that can evolve separately. A second thing, which I think the participants really sort of like got during the seminar, but people who were not either alive or even teenagers or adults during the time, was that the economic basis of the development of the internet was not commercial. It was paid for by research money provided by public funds. And this parent pays model funded both the rapid development of the internet and nearly free connection, or free connection in many cases, to the net for a large number of people before any commercially viable applications like e-commerce applications or later social networking or search or any of those information access technologies became popular. And that allowed the internet to reach a certain critical mass worldwide, at least US and Europe, perhaps, maybe a few other places, before it needed to depend on infusions of large amounts of money from the commercial sector. And then third, the regulatory environment, there were two aspects to this. One was that the gods, so to speak, of the internet managed to avoid any kind of regulatory capture by the de jure standards community. It went in parallel. It told people like the CCITT and the ITU to go, go do your thing. We don't care about you. We're going to do our own thing. And we're not going to depend on any kind of de jure blessing of what we're doing. And this was happening at the same time that fairly rapid deregulation of telecom was happening, which in some sense damped the ability of the telecom industry to come after us. So the thing to ponder there was, is this a one-time event that will never happen again? Or perhaps we may see a recapitulation of this if a bunch of things come together. Now, next slide. So there are obviously a whole lot of problems. And I would say from a technical standpoint, we have a lot of ossification in the protocol suite. And the introduction of stateful intermediaries has seriously limited many future design choices. And it locked in inefficiencies that keep things from tracking advances in communication services. Now, part of that is not purely technical, because one of the characteristics of the classic telecom industry, which sort of reared its ugly head again, was it was important for people to try to introduce themselves into the value chain for moving data around without actually adding significant values themselves. So that's why we see, to some extent, other than the security things that might get covered by Craig and others, this proliferation of stateful intermediaries that make it very, very hard to evolve the end-to-end part of the system because they run afoul of assumptions that should never have been made by those intermediate things. And from an economic standpoint, back in the early days, you didn't have to have a solution that scaled to 1 billion endpoints in order to be taken seriously. And today, because the system is global, worldwide, and with billions and billions of endpoints and hundreds of thousands of switching points in the network, someone who proposes something for global rollout, you need to be perceived that you can scale to that before you're ever taken even moderately seriously. That, together with the rapid centralization of the infrastructure and the application services into a, I would say, distressingly small number of commercial entities, means that only those entities seem to have the ability to roll out anything new on a global scale. And that's clearly slowing things down. And then lastly, from a regulatory point of view, with a medical analogy, our standardization efforts have sort of gotten into the first do no harm mode, in the IETF and potentially other places, which means that any kind of fast innovation is very, very hard to move out, because anytime something new that may change the dynamics of the global system is proposed, the obvious and important question comes, what are you going to break? And this was recognized probably at least 15 years ago. And the NSF and some communities in Europe and the research community tried to got funded and tried some clean slate designs in order to sort of break this ossification characteristic. And some of them were really super cool. Matter of fact, I think all of them were probably super cool, but they didn't go anywhere. And they didn't even really influence the existing protocols in a meaningful way. So a question I think that is sort of global for the research community is there an alternative approach in networking research in order to get things that are going to have important, good effects going forward? Next slide. So all of us were asked to sort of look back in history and pick some things that we really should have done differently. We should have known better, and we got wrong. And there are a bunch of those. We can argue, we argued a lot back and forth as to the relative importance of many of these. And I had a list of probably 5 or 10 that in retrospect, I think we probably got wrong. But I want to highlight one of them. And that was the fact we allowed a bunch of Berkeley graduate students to define the API to the network. And they got at least one thing massively wrong, which was get host by name and the other Berkeley sockets calls that exposed IP addresses to the application layer. This was, I think, a pretty serious mistake. And in my view, it's one of the, but certainly one of a few fundamental causes why we couldn't roll out IPv6, because we couldn't change the addressing in the network layer without breaking all the applications, because the applications got to see IPv4 addresses and pretend that they understood them. So we couldn't change the addressing. And when you have to change 2 critical parts of the system simultaneously and globally, that becomes an almost insurmountable problem. And we still don't have IPv6 actually completely rolled out. And many of the application hosts still don't support IPv6, particularly in the area of IoT systems or things like TiVos and DVRs and stuff like that. A second really bad consequence is that by exposing IP addresses, we expose multipath and connection rebinding on top of the transport layer. This made any kind of multipath transport extremely hard to deploy. If you look at the trajectory of MPTCP, you saw that this got extremely complicated, and the applications had to interact directly with the ability to support multipath. And we still don't have multipath capabilities in QUIC. They've been taking years to define. And lastly, of course, if you expose lower layer addresses and allow applications to pass them around, this opens up a gigantic attack surface because it makes reflection attacks trivial. All you have to do is take somebody's IP address, send it to a third party, and convince them to bomb them. So there's a general principle I'd like people to ponder here as we go forward, which is I think we need to be way more careful about allowing layer violations. Because you may think it's a small thing that allows you to do some optimization above the API that's hiding the abstractions of the lower layers. But later, potentially years later, they can come back and bite you. So thanks.
Hey, great, Dave. Thanks. Craig, you're up next.
Yep, sorry, the mute button moved. Hi, everybody. I'm delighted to be here. I'm going to start off with a quick philosophical point, which isn't on my slide, and then jump in. I know we're already running a little long by Jim's standards, so I will try to be a little brisk and buy us some time. So Dave Sinkowski, a friend and a long-time telephony researcher, said something I thought was profound, if a little optimistic. He commented that there only about once a generation, and I think maybe he was too optimistic. I think it may be once every 2 or 3 generations, do you get to revisit your communications infrastructure and really redo it? And, you know, thinking about the evolution of the telecommunications system, and before that, telegraph to telephones from analog to digital, all those sorts of things. The internet was the sort of generational transformation that we got to live through. And you know, it's as several people have already pointed out, it's a very narrow window of time. A lot of things come together to make that change possible, and we were able to seize that moment and do it. But on the other hand, some things didn't survive so well. And indeed, much of the Dagstuhl workshop was talking about why did we end up in various architecturally ugly places today, and where might we have done better? And I'm just going to briefly talk on two that came up a fair bit, and you actually heard some of this in Dave's talk. Next slide, please. So the first one is security. We actually went around this one several times. People kept asking, why wasn't security more integrated into the internet architecture? You know, and one of the key things, of course, was because at the moment the transition was happening, much of what we now think of as completely standard security thinking did not exist at the time. So we understood encapsulation. People were building the equivalent of IPsec devices for the military at the time. And we understood the essentials of public key encryption, which was invented concurrently with TCP/IP. But the notion of security associations, the ability to do per packet encryption instead of taking all the packets coming in on one side of the box and spitting them out as encrypted IP datagrams inside another IP datagram, those came later. Furthermore, people tend to forget that it was deep into the 90s before we were free to email code around, to ship code around. We could ship printed copies, we could ship the papers describing the algorithm, but we couldn't actually send you the code implementing the algorithm. And indeed, even creating code points that you could slip your code into was restricted. So in many ways, security for public policy reasons was a vast, sticky mess that we didn't want to get into. Now, the other, and indeed could not, the internet succeeded in part because we didn't go stepping into that mess. The other one is firewalls. Firewalls, we could have probably done better. I don't claim to know exactly how we would do them better, but I will say that the situation was that we completely ignored the fact that all sorts of cruft was showing up on our networks. Dave Mills specialized in creating names for these things, such as Martians, for packets that had no business being on your network, but you found them there. And we just ignored that. We knew it. It was sort of considered amusing, but not a problem to be solved. And by the time the security issues came crashing at us because we were letting all sorts of crap show up on our networks in ways that we shouldn't, it was late in the game, and we had to race towards the obvious solution, which is to create a box that sits there and basically audits all of your packets and enforces their correctness, which means the box needs to know all the protocols. And at that point, suddenly, it's very, very hard to inject a new protocol into the network at layer 4. It's very hard to add new options to layer 4 or layer 3. And these firewalls are by a bunch of different security vendors, so they're scattered around the network, which means that we sort of have the inverse of the n-by-n rule, which says basically don't invent a protocol where adding one new protocol means I have to go update all the devices at the edge independently. Well, that's exactly what we created with firewalls. I mean, we got ourselves caught in that rule in the worst way. We violated it. All right, next slide. Whoops, we went 2 ahead. There we go. The other mistake that we clearly made were IP addresses were too small. The fact that we blew through them in 10 years is a pretty good indication. Another indication is that at the same time, the folks building designing the Ethernet address space were looking at the possibility of how many Ethernet cards they would ship and all that sort of stuff. And they were looking at 6 bytes. Now, 6 bytes probably still wouldn't have been long enough, but the point was the internet picked smaller, and that was a mistake. So we were rapidly forced into network address translation. And combined with the fact that Dave pointed out, IP addresses become first-class objects, this meant that we had another box there beyond firewalls that's looking through the packets, in this case, desperately to clean up IP addresses that have to be changed by the translation. Again, it makes it extremely hard for you to change the protocol space. So you sort of lock yourself into this terrible mess. So I'm going to stop there and hand it over to Henning, because as I say, I was trying to make up some time. And
Okay.
look forward to the questions.
Okay, great. We've got a lot of questions coming in on the webinar chat. So Henning, you're up.
So one of the reasons I think the internet turned out to be successful is because I think it passed the homework assignment test. Namely, I believe a good algorithm, a good protocol in our domain has the property that you can build something that is simple enough that you can assign it as a 2-week computer science undergraduate homework. And you can actually, in a networking sense, build something that is at least roughly conforming to a subset of an RFC, and you could achieve interoperability within the course you're teaching. And when I've been doing that in classes I teach, and it tends to work relatively well, where we all build kind of as an assignment, like an HTTP subset or an email protocol, or you can even do that with SIP and so on. So you're talking hundreds to maybe thousands lines of code if you're, so maybe a team project at that point. And that's what I think we have evolved in, is that because these initial subsets turned out to be not quite industrial strength, they lack controls and don't handle many of the corner cases that we would like to, we have evolved to a patch model of protocol evolution, where basically a lot of the old protocols, say TCP or email or so on, are basically or DNS most famously, are a series of RFCs that partially update earlier RFCs in often non-obvious ways. So now it becomes increasingly difficult to build an industrial strength application, so that it goes from a class project to essentially a multi-person project that only a few entities can actually successfully complete, and where we're stuck with a very small number of core implementations, say 2 or 3 for like DNS or HTTP at any given time, that dominate the market. There are many HTTP server implementation, but I mean, we're still doing Nynx and Apache basically for most of the public-facing ones in that, and it would be quite an effort and unlikely to succeed if you were to replicate that. As a related thing is that the initial part of success of allowing kind of the undergraduate quality of code to define the internet also is what we know generally now as Pastel's laws, namely the liberal part in that, namely be liberal in what you accept, also then has led to 2 very undesirable consequences, namely many of the vulnerabilities that still dog our network protocol implementations are most likely in the parsing part, because that's where the outside world can attack us. And that's why we got the firewalls too, to basically protect against these less than robust implementations in that. And it means that our code base, particularly for some of the core protocols like routing and email and to some extent web and others, get much more complicated, because we have to still handle, say, email addresses that haven't been actively used for 30 years. Next. So the next one that I think is a more recent one, and I think, Jim, you're giving your related talk, which focuses more on the SDN side, but we all enjoy now the ability to rapidly deploy software across many different venues, both automated software distribution as well as kind of your browser as an automated software loading tool for JavaScript and other things. Oops. Can you go back just a second? Yep. Which means that because we can install applications, that the only applications that are still mostly compatible are a small subset, namely email, web for rendering pages, and calendaring as an email attachment. Other things where, like, we are using Zoom, which is a proprietary closed application in that doesn't interoperate with anything except kind of has some SIP interfaces at the edges in that. So that's actually compared to, since the early days of telecom was mentioned, is actually a regression. Namely, in many ways, we had better interoperability at the application layer during the early days of SMS than we do now for messaging. See the famous green and blue bubble issue. We had better interoperability for faxes than we now do for many messaging and transmit application. That's why doctor offices still use them. We haven't really standardized a new application in 20 plus years. And so that's largely because what vendors didn't used to be able to do is they can now install applications very easily, which means the need for interoperability has greatly diminished which was largely because you couldn't reasonably install stuff on the other side. And so you had to agree on the packets that you exchange. So is that something we can fight? Do we want more one? And it may well be, as the MIMI effort and the IATF shows, that it may take regulatory intervention, just as it did during the antitrust trial for Microsoft, to open up APIs and protocols. Next. And if I could change one thing, this is one of several that like for all of us that we talked about, is that we have evolved essentially a set of important critical control type of protocols that don't transport data, but without which the internet cannot function. All the way kind of from DHCP to classical and more network management to routing. All of these protocols have evolved completely independently, as in they use different encodings, they have different security mechanisms that don't interact with each other, and they use different transport protocols. And so every time you want a new transport protocol, you have to fundamentally modify what's on top. And they just don't behave, they can't be managed separately, the identities don't align, all of that. In a world where we could A, change things, and B, where we could go back and maybe kind of alter the course of history, we would recognize that all these control protocols share core functionality that would have been much better if we had a shared code base and thought about, yep, we need some distributed database of something, which is kind of DNS, except it's not quite general enough. We need a way for ASs to exchange information. We kind of have that called BGP, but it really doesn't exchange all the information we need. So we do all kinds of strange stuff to do that, and so on. So having a common way of managing the control and upper layer type functionality at all layers would have simplified the network and allowed better security in particular, because we could protect identifiers and other components. And with that, I'm handed off to the next one.
Okay, Jörg, you're up, and I'll encourage you to follow the Craig Partridge model of 5 minutes, because we've got a bunch of questions that I've got queued up from the comments.
I will try to. I want to follow up on Henning's complexity points and maybe touch upon one lesson not so much learned over the past 20 years, at least as I can tell from my work in mobile and mobile communications and mobile network access. And that is whom we are actually building the internet for. So IP has baked in fundamental assumptions of everything being always connected. People use RPC for all kinds of bits, assuming that they would never fail. So we make strong assumptions about things being connected, and always also being connected towards a core where you can go to backend towards backend services, which means not so well, not permanently connected or isolated entities might not be easily workable in an internet infrastructure. So you have to gear up additional thoughts that might not be super compatible. So this is one of the things that seems to be coming back over and over again. And a secondary issue of this connectivity bit is that this connectivity is also assumed to be at high performance. And governments have been looking at what's the minimum required access link capacity in order so you can call it broadband and you can meaningfully use the internet. And over time, while in the beginning, our applications might not have been as demanding, applications grew, became more demanding, user experience governed, and so on. And so we also now have seemingly seem to be forgetting the lower end of the scale of internet to whom we would like to provide internet services. This comes at a time when people try to reach out to the next billion or what next 3 billion, next 5 billion or whatever users who might also have their expectations on how things perform. Whoever has recently tried to access any internet service over an edge cellular connection when connectivity wasn't great probably has a good idea of what I'm talking about. Next slide. One interesting bit that was talked about with middle boxes and so on, that we lost the ability to easily innovate end to end. We also have, we still do have internet end-to-end connectivity, but we also have many entities, CDNs and hyperscalers who run their own global networks. So one of the things that we also observed that user interactions for the sake of performance or whatever always happen endpoint to cloud, so we don't even traverse the board of the internet anymore. So to a certain extent, you could argue that this, if taken all the way to the end, this might reduce TCP/IP to effectively being an API to get to the closest whatever service entity you might have, which may not be that desirable. Maybe it is desirable, I don't know, but this is at least one of the risks we may be running that we have been pondering about a bit as well. Interesting implications for services and content. We discussed quite a bit the issue of fragmentation, having different local views of an internet, different countries run their own flavor of an internet. Censorship, an interesting question is referability or transitivity. Can I give you a URI or some other link and you are going to see the same content? So that's an interesting question that came up a bunch of different times, and it's unclear where we are heading and whether the path we have been embarking on so far is actually desirable. Next, last one. I'll try to be quick on this one. Effectively, maybe because we're mostly technology people, and the fact that the technology itself doesn't really define or limits its future usage has come up many times, and we often went off into quite a few non-technical discussions that are not always easy to be had. The IETF has often quoted, we try to do mechanisms and not policies, but at the same time recognizing that it's not super easy to just do technology because your choices may, to a certain extent, impact what you can do with this in the end. Interesting enough, as an surprising outcome is to a certain extent centralization, because the internet protocols themselves are mostly inherently distributed. But today's deployments aren't, as we have been hearing repeatedly, maybe for economies of scale, maybe for convenience, maybe for simplicity, maybe because things have gotten so complex that you can't, that individuals can't rely on building them themselves or managing them themselves anymore. The same roughly applies to content, where on the one hand, we might have seen, or we could have imagined the democratization of networks with many voices being heard. We have also seen that this has effectively led to disinformation and all kinds of other issues dominating at least social media networks. And the final point beyond technology that was also briefly mentioned is governance. So the IETF, Dave put this nicely in the beginning, had a very different approach to dealing with standardization in apostrophes and compared to ITUT and other de jure organizations. Some people feel the IETF got more rigid and less flexible over time. At the same time, the question still remains whether we actually have scaled up its capabilities with internet size and importance and speeds of development, but that certainly also holds for governments and other and regulations who may set the frameworks for stuff that we have to do. And with that, so these were discussion points that we picked up repeatedly. But I want to close with that.
Okay, great. Well, thank you all. Wow, that was really fabulous. Golly, there's been lots of questions. We've only got about 10 minutes, so I'm going to pick two of them and phrase them for you. I'm sure with your comments as teasers, people are just waiting on the edge of their seats for your report to come out. Okay, first question. So, John, back at the very beginning, you talked about open source, but there were some comments about open infrastructure that you made, and I saw a couple of others as well. And the fact that who owns the infrastructure allows you to do innovation. And one might contrast that with the situation in 4G and 5G infrastructure, except maybe for CBRS, just in terms of the openness of the infrastructure. Larry Peterson posted an interesting blog post a couple of days ago on democratizing 5G. One might make some of the same comments about some of the hyperscalers and some of the closed environments there. Does anybody have any? So those were some observations that sort of came through. Anybody want to comment on that, about the openness of the infrastructure, not so much the openness of the protocols? You could just talk all over each other.
Oh, okay. Well, I mean, so yeah, the evolution of cellular protocols is fascinating to me, because essentially what goes on is for each G, you publish a laundry list of services that you were basically throwing up to see where the money will flow. So this is John's point about your routing money. The G protocol, 3G, 4G, 5G are all about routing money. And so what you do is you say, I have a Ginsu knife, for those of you who are too young to remember, this was the ad that was running in the middle of the night when we were still stuck with television channels, and somebody found a way to pretend there was an all-purpose knife that could do everything. That's what the G protocols are. And then they only implement a subset. And since the question of what subset is supported is determined by the carrier, because they control the gateways to the larger internet, you're screwed. And yes, we should be trying to open that up. We should also, but the problem is then we're going to have a huge regulatory standards fight about, well, which services are we going to support and who are we going to disenfranchise, which is not necessarily true. What we discover is if you build the right infrastructure, people find a way to use it, but they'll feel disenfranchised. And we're in the political layer, the famous layer 8, right?
So let me ask Henning, Henning, since you've been in the FCC and now you're at NTIA and Commerce, I'm sure you have reflections on what Craig just said.
Yeah, and I mean, I think one of the ways that I think about this is that we live in and Jim and I and maybe others examples of that, we live in houses that were built in the last century and that are close in order in the internet in many cases. They're comfortable and they do their job, but we would never build them in quite the same way. And the industry has found that operating comfortable network is much more productive and economically efficient than building new networks in that. And so that's why airline design hasn't changed since the 1960s really in dramatic ways in that. So I would argue that and this came to the economics one, is that the economics of new things, even if we were to start anew, would be different, is mainly about how can we reduce the capital expenditure. How can we operate an environment where we don't have a whole lot of trained staff that have PhDs? They have all moved on to the AI side of the business. And how can we operate that in a way that we don't have to train people every 10 years on new stuff? We can, and it's good enough type of model in that. So it's really been, in the NTIA side, we're deploying, getting broadband network deployed across the country. Nobody's talking about new architectures, except maybe at the fiber layer in that. But people are talking about manageability in that. It is really about managing the operational cost of it that's driving it. It's not capabilities. It is not beauty. It is not any of the other things that we might care about.
Okay. We've only got a few minutes left, so I want to get one more question out there and remind people that we'll continue these conversations on the Slack channel. And this is sort of a combined question that came in through separate comments by Randy Bush and Christophe Dio. And it has a little bit to do about, Craig, I think you made the point about no security early on and that things never would have gotten started if there had been security from day one, but maybe security became a concern a little bit too late, whereas something like congestion control seem to have been invented sort of just in time. And so just your thoughts on, necessity is the mother of invention, but can you, are there other cases, or in these cases, do you think earlier would have been better, or just in time? Are there other examples like that?
There was a query on the channel, which I answered. Network management. We had proprietary network management protocols from the very start. Nobody sat down and said, what should the general purpose network management protocol be? And when the network suddenly blossomed with NSFNet, we found ourselves with no interoperable network management protocol. And the answer is basically we got SNMP because that was what we could cobble together from what we understood in a matter of weeks and deploy. Even though the moment we deployed it, people had a laundry list of things that SNMP could not do that they needed. And we have had to deal with those known consequences ever since. And this, so, there are cases where that just didn't work out. And there are other cases like congestion control where it mostly did work out, that we figured out at the time.
So I'd like to, at least for managing the network itself, as opposed to the applications on the network, one of the things we struggled with, and I think still struggle with, is when you have a network that is operated by multiple mutually distrustful administrations, also vying for money, there's a tension, a very strong tussle between what information you are willing to allow your competitors to see about how your network is operating versus the ability to debug anything in a multi-administrative system. And we saw this in routing itself with BGP. We didn't learn much of a lesson from that, maybe a little bit, but we learned even less of a lesson in terms of what we needed to cause people to expose about their networks in order to be able to manage things.
Okay, John, Jörg, any last thoughts on either of those or anything?
Well, I want to go back to the security question and just say something that Henning has also raised in the chat, which is security isn't a thing, right? Congestion control, you can kind of point to the goal. That's fairly clear. There's a lot of nuance for sure, but security is an ever-changing space in which, whatever problem you solve today is going to turn out to be the wrong one tomorrow. So I think that the question, as you posed it, is a very challenging one, because it's really raising things that are at two completely different ends of the spectrum, and understanding how those things relate to evolution is important.
Fair enough.
Maybe just to add a bit to this, it might have been hard to find to identify the security goals or threats or issues that we had encountered over time 40 years back, in order to make meaningful decisions to bake them into an initial design. That ties a bit in with what John just said, and what Henning typed, that security is more than just packet encryption, but actually in trying to understand in a friendly environment what you're trying to defend against is just way harder compared to now that we have plenty of experience with all kinds of issues.
Mm-hmm. Okay.
And actually, there's one more point to add to that really quick, which is it's having a allegedly simple core of the network is actually really helpful here, because it means that the defenses can evolve without having to change the whole network.
Okay, I think with that comment, John, we're 1 past the hour, so we're gonna call it close here. I'll remind everybody again, we're gonna move things over to Slack. I want to actually, maybe before I thank everybody, I want to remind folks that in 2 weeks we have another networking channel event, and I'm just gonna very quickly share my screen here to show what that is. There we go. There we go. Next event coming up, Green Digit, about carbon, about energy. I think it'll be great. Again, 2 weeks from right now at exactly the same time. And with that, honestly, I want to thank the 5 of you. It was just totally awesome. You can look at all the comments in the chat about how much people appreciated this. We really appreciate the time and the thought. Please join on the Slack. We're going to copy over all the comments and questions, and we can continue the conversation there. So Thanks, everybody, for joining in. See you in 2 weeks.